So for 19.2, this is where all the calculations with pH, pOH, hydrogens, and hydroxides come into play. So we're just going to review how to navigate through each of these calculations. So let's say, for instance, we are given the amount of hydrogens in a solution. Well, if we want to go in this direction and figure out the pH, then what we would need to do is negative log of the amount of hydrogens. Let me write this a little darker. So if we're given, again, if we're given the hydrogens and we want to find the pH, so in other words, we want to go in this direction, we just do negative log of the amount of hydrogens. If we want to go backwards, let's say you're given the pH and you want to find the amount of hydrogens, we would do 10 to the negative pH, where the negative pH is as an exponent. Okay? Likewise, if we have the amount of hydroxides and we want to go to just the pOH, we do negative log of the hydroxides. Okay. If we want to go from pOH back to the amount of hydroxides that it came from, we do 10 to the negative pOH. So you notice these two equations are very similar. This one deals with hydrogens, going from hydrogen to pH. This one deals with hydroxides, if we're going from OHs to pOHs. Okay, so how do we convert between these two and these two? So for pH to pOH, if we know the pH of something, we can always find the pOH, and this is going to be a double arrow. We can go back and forth, as long as we keep in mind that pH plus pOH always equals 14. So if we know one of them, we can just subtract from 14 to get to the other. Likewise, for these guys, if we want to go back and forth between hydrogens and hydroxides, we should know that hydrogen times hydroxide always equals 1.0 times 10 to the negative 14. Okay, so again, the amount of hydrogens is always, hydrogens times hydroxides always equals 1.0 times 10 to the negative 14. In case they were to ask on a test, this is called sometimes the KW, which means it also can be called the ion product constant of water. So what does that mean? An ion is something that has charges. This is H plus and this is OH minus. Those have charges. Product means to multiply, so these are ions that we're multiplying together, and they always equal a constant number. They always equal 1.0 times 10 to the negative 14. So these are the calculations you definitely want to be familiar with, and we'll do a few examples so that you can figure out how to navigate between these. Okay. So let's say, for instance, you are given a problem that says something like this. Let me write it up here. Okay, so not so many words, but let's say we're given 0.05 molar of sulfuric acid, and the question is how much hydroxide is in the mixture. So we have the molarity or the concentration of the acid, but they're asking about hydroxides. So in other words, we are given the amount of, we can figure out the amount of hydrogens here, so we're technically at this step, and they're asking about this one. So if we're here and we want to go here, first we need to figure out how many hydrogens we have, and then we can convert it over into hydroxides. So how do we do that? One thing to keep in mind, this is what we call a diprotic acid. H2SO4 has 2 hydrogens, so this is diprotic. Anytime you're dealing with something that is diprotic or triprotic, you have to take into account the amount of hydrogens. Just like if we had a base that had more than 1 hydroxide, we want to take that into account as well. So because we have 2 hydrogens, we have to multiply the concentration they give us by 2. So really we're dealing with 0.1 for our hydrogens. We have 0.1 for the concentration for hydrogens. So if we switch down here, if we have 0.1 for the hydrogens, then the actual equation we would end up with would be the amount of hydrogens we have is 0.1. We don't know the amount of hydroxides, but we know that those two together always equal 1.0 times 10 to the negative 14. Okay. So simply all we need to do is just divide by 0.1. So then that would roughly give us that the amount of hydroxides is 1.0 times 10 to the negative 13. Okay, so very simple. Once we know the amount of hydrogens, we can just divide to find hydroxides. Let's say if we flip back up here, let's say the question didn't ask for hydroxides, but instead asked for the POH. Okay, well, if it's asking for the POH, we're starting here. We'd be starting here with the amount of hydrogens, and we'd have to skip all the way up here to POH. So we have two ways that we could do that. We could first go from the amount of hydrogens to the pH by doing negative log, and then we could switch over that way. Or we could find out the amount of hydroxides and then jump up and do negative log of that to get to the POH. So sometimes memorizing the formulas in this format makes it a little bit easier for you to figure out what steps you can take to get to the final answer. So let's say we go this route. Let's say we have the hydrogens, which we calculated to be 0.1. Remember we said there were 2 hydrogens here, so we had to double this amount. So 2 times 0.05 gives us 0.1. So now that we know the amount of hydrogens, let's go ahead and actually find the pH. Okay, so to do that, erase this here, makes a little more space. So we would just do negative log of 0.1. And that would give us a pH of 1. And then, if we're here, we know the pH, we can easily go to the POH by subtracting 14 from that. So we know pH plus POH equals 14. Well, we just found out that the pH was 1. So then that tells us that the POH has to be 13. So the good thing about this, if you think about the equations in this format, we're at most going to be doing 2 calculations. If you're here for hydrogens and you got to skip all the way over here, you just got to go either one step and then convert to the second step, or we could go this way, convert to hydroxides and then go up that way. So if we were to have gone from hydrogens to hydroxides to POH, let's look at how that calculation would have been. So we would have wanted to have figured out the amount of hydrogens, which we said was 0.1. We know that the amount of hydroxides times the amount of hydrogens always equals 1.0 times 10 to the negative 14, which means that the amount of hydroxides is 1.0 times 10 to the negative 13 if we would have divided by 0.1. And now that means we would have been at this step. Now we want to go from here to here. So if the amount of hydroxides is 1.0 times 10 to the negative 13, we would just need to do negative log of that number, and that would give us the POH. And it's giving us the POH because we're dealing with hydroxides. And so the POH would have been 13. So we would have ended up with the same answer. Okay. So just be comfortable converting between these calculations. If you're given just the hydrogens and you need to go to the pH, you just do negative log of that number. So let's look at one example where we're given the pH, but we're asked about the hydrogens. So let's say they say you have a solution that has a pH of 4.5, but you want to know the amount of hydroxides. Okay. So we are here with pH, but we want to skip all the way over here. So to go from here to here, we can go to hydrogens first and then to hydroxides, or we can go from pH to POH to hydroxides. So let's take the route at the top and go that way. So first, to go from pH to POH, we just need to subtract 14. So if the pH is 4.5, that means the POH is going to be 14 minus 4.5, which means the POH is going to be 9.5. So now we've gone from pH to POH. Now we can go into hydroxides. Well, if we want to go from POH to hydroxides, we just need to do 10 to the negative POH. So if this is our POH, we're just going to do 10 to the negative 9.5. That would give us the amount of hydroxides. And then whatever this number is, you enter it in on your calculator, and the negative 9.5 as an exponent. that would give you the amount of hydroxides. Okay? So it may be helpful just to memorize kind of this diagram, and that way it can help you figure out how to do the calculations. Okay. All right, so let's review kind of what pH and pOH and all of this stuff is. One thing to keep in mind for the pH scale, and that's the scale that runs from 0 to 14, that is based off of the pH. So we know acids are things less than 7, have a pH less than 7. If you have a pH of exactly 7, you're neutral. If you have a pH greater than 7, you're a base. But this is the pH scale. So the reason why I emphasize that is if you're given the pOH, you can't use this to find acids and bases. So for example, if something tells you that the pOH is 3, you can't say, oh, well, that's less than 7, this is an acid. We're not going to say that. Because this is the pH scale. You have to know the amount of hydrogens in order to be able to figure out if it's an acid or a base. But this can help us though. If the pOH is 3, that means the pH must be 11, because remember these two should always add up to 14. Well, if the pH is 11, now we can figure out where we are on the scale, and 11 would be somewhere here, so that makes us a base. Okay? So keep in mind, the pH is what you use to figure out if you have an acid or a base. All right. One thing to also keep in mind, a lot of people get confused that they think acids have hydrogens and that's it, and bases have hydroxides and that's it. That's actually not true. No matter the substance, whether it's an acid or a base, they both have hydrogens and hydroxides. The only difference is acids have more hydrogens than they do hydroxides. So they have a greater amount. Things that are neutral have an equal amount. So they have an equal amount of hydrogens and an equal amount of hydroxides, which makes them neutral. Bases, they also do have hydrogens even though they're not acids. Bases just have fewer hydrogens. They have less hydrogens in comparison to their hydroxide. Okay, so just keeping that in mind. For any substance, no matter if it's an acid or a base, we can find pOHs and OHs for acids, just like we can find pHs and hydrogens for bases. They both have both of them present. It just depends on how much more you have. Acids have more hydrogens than hydroxides, and bases have fewer hydrogens than hydroxides. Okay. One other thing to keep in mind with pH is that the more hydrogens you have, so the higher your hydrogen concentration, or the more hydrogens you have, the lower your pH. And that's kind of confusing. The more hydrogens you have, your pH would probably be close to 0 or close to 1. The fewer the hydrogens, then you're probably going to be more of a base. You're going to have a higher pH. So the lower the amount of hydrogens, the higher the pH, which means you're a base. Okay, so just kind of keeping that in mind. You may get some concept questions related to that. That's pretty much 19.2 to review, but I would definitely recommend doing several different calculations using kind of that diagram that we just looked at to make sure you can do those ones that may be 2 steps. One other thing to keep in mind for the pH is that let's say you're given something that has a pH of 10 versus something that has a pH of 14. Okay? These are both bases. Okay, they're both bases because their pH is greater than 7. But who would be the stronger base? So between these two, this is definitely the stronger base. The higher the pH, the stronger the base. The lower the pH, the stronger the acid. But this is a stronger base. Well, the question may be, well, how much stronger is this base in comparison to this one? Well, a lot of people may say, this one, this pH of 14 is 4 times stronger. Because 14 minus 10 is 4. That's not entirely true. One thing with the pH scale, it's in groups of, or each unit is actually a factor of 10. So if we're here at 10, and we have to go 11, 12, 13, 14, that's 4 units. That's 10 times 10 times 10 times 10 distance between them. So that's actually 10,000 times stronger, not 4 times, 10,000 times stronger. Now the 4 would be helpful. Now one way that we can figure out the strength of acids and bases is the units that separate them. There's 4 numbers or 4 units that separate these guys. That actually is the exponent. So that means that this is 10 to the 4th times or 10,000 times stronger. If these pHs were instead, let's say, pH of 1 versus a pH of 3, well, that's a unit of difference of 2. Now, these wouldn't be bases anymore, these would be acids. So if you have a pH of 1 versus a pH of 3, that makes you the stronger acid. Lower numbers make you stronger acids. Higher numbers make you stronger bases. Now, if we wanted to figure out how much stronger of an acid this one is, the distance between 3 and 1 is 2. We dump that in as the exponent. This is actually 10 times 10 or 100 times stronger than a pH of 3. So just be careful with that. Each unit is a factor of 10. And we multiply those guys together. So if you're 2 units away, it's 10 times 10. If you're 4 units away, it'd be 10 times 10 times 10 times 10 times stronger. Okay, so the next thing, if we want to go into 19.3, it's a good segue. 19.3 deals with strong acids and strong bases and kind of knowing what's strong versus what's weak. Now, one thing that you will have to memorize is which are the strong acids and which are the strong bases. If we start with the strong bases are really easy to memorize. Now remember, the base formula is always a metal with hydroxide. So if you use for your metal something from the first or second column for your metal, then that means that you have a strong base. So like if you were to use lithium or potassium or calcium or strontium, any of those from the first 2 columns, if you use those for your metal and you put it with hydroxide, you have a strong base. Just to kind of review, things from the first group are called alkali metals. So if you use alkali metal, that makes it a strong base. If you also likewise use an alkaline earth, those are the ones from the second. So if you use any metal from the first or second column with hydroxide, that makes it a strong base. Now between these 2 groups, the first group is stronger. So anything that's in the first column is the strongest absolute base. Second column is pretty strong, but not nearly as strong as the first one. Okay, strong acids. There are only 6 strong acids, and I'll write the 6 out here. If you're given an acid and it's not one of these 6, it's automatically considered to be weak. So the strong acids are HCl, and remember there's only 6 of them. So HCl, HBr or hydrobromic acid, hydroiodic or HI, nitric HNO3, sulfuric H2SO4, and perchloric is the last one. That's HClO4. So you will definitely need to know that these are the 6 strong acids. If it's not one of these 6, so if they give you something like HF or HC2H3O2, which is acetic acid or vinegar, these are weak acids. Okay, if it's not one of these 6, it's automatically weak. It's going to be very important for you to know what are strong acids and what are strong bases. They could, for a question, give you a random acid and ask you if it's strong or weak. Well, to know that, you'd have to know which are the strong ones. Right? If it's not one of those 6, then it's automatically weak. One important thing to know about strong bases and strong acids is that when we dissolve them or we put them in water, they completely separate. So if we look at what happens with a strong base, okay? Bases are ionic compounds because it's a metal and a non-metal, so bases are ionic compounds. And we have this fancy word that we use to describe when ionic compounds separate. We don't say separate and we don't say decompose. We say that they dissociate. And that's just a fancy word that we only use for ionic compounds. So if we have a base, something like NaOH, sodium is in that first column, so this is a strong base. When strong bases get added to water, they completely break apart, literally like right down the middle, into the metal and the hydroxide. Okay, and we would just say that this dissociates. And again, we said that's a special word that we use for bases or ionic compounds. Okay, if we're dealing with strong acids we say ionize, and it just means separates. But for acids are covalent compounds. And covalent compounds, we don't say dissociate. Dissociate is only a word we use for ionic compounds. For covalent compounds, we say that the ions or the compound ionizes or separates. So if we take something like HCl, which was from that list of 6 strong acids, that's going to completely ionize or break apart into just hydrogen and chlorine. Okay? So only strong bases and strong acids completely separate. Strong bases can dissociate or break apart into their pieces, and strong acids can ionize into their pieces. So you might say, well, what happens if you have something that's weak? Well, let's look at what happens with weak bases and weak acids. So we can still use those words dissociate or ionize. They're just going to behave a little bit differently. So let's look at weak bases and weak acids. Okay. So a weak base would be any base that has a metal that's not from those first two columns. So let's say we have aluminum hydroxide. Okay. That's going to break apart into aluminum and 3 hydroxides. And this 3 that's here came from the fact that aluminum had a +3 charge. But that breaks apart this way, but it's a weak base. So what actually happens is we have an arrow going the other way also, which means some of it will break apart or some of it will dissociate, but a lot of it will go back to being stuck together and go back to being in this form. So for weak bases, and the same thing we'll see for weak acids, they don't just go in one direction. They can go over here and break apart or dissociate, but then they're going to immediately go back and be stuck together again. Okay? So they can't really separate from each other. They want to stay stuck together so they can go back and forth. Strong bases completely dissociate. They will not go back and being stuck together. They prefer to be separated. So if we look at what happens for a weak acid, let's say we have HF. It's not one of those 6 from our list. So it will break apart. Some of it will ionize or separate. But as soon as it separates, it's going to go back to being stuck together. So they prefer to be stuck together instead of separating. So these double arrows, we really only use when we're dealing with weak bases or weak acids to show that they don't really separate when we try to dissolve them. Okay? But you won't know how to draw your arrows if you don't know whether you have a weak base or a strong base, or a weak acid versus a strong acid. All right, another thing that we want to look at, and this is more so 19.3, strictly concepts, no calculations involved with this, is that we have something called the Ka and Kb. Ka is the acid dissociation constant. So it's a number that helps us figure out how much things may break apart. Same idea with Kb, it's called the base dissociation constant. So it's a number that helps us figure out if something is going to separate or not. Okay? The way that this works is the higher the Ka value, that means the stronger the acid. Okay? So the higher the Ka, that means you really want to separate, you really want to dissociate. So that's what acids do, they want to break apart from each other and be separated. Same idea for this guy, the higher your Kb for bases, the stronger the base. The higher the Kb, that means you really want to be broke apart, you really want to be separated, you don't want to be stuck together. The lower the Ka, that means the weaker the acid. That acid really prefers to be stuck together and it doesn't want to dissociate, it doesn't want to separate. And the lower the Kb number, the weaker the base. So you may ask, well, what's a low number versus what's a high number? What would be considered low versus high? High Kas and high Kbs are things that are probably between 0.1 and 0.001. Those are considered to be relatively, in chemistry, we're used to dealing with small numbers. So a number between 0.1 and 0.001 is considered a relatively big number. Okay? Of course, they could give you a Ka that's like 5 or 50 or 1,000, but that's usually not likely. Usually we deal with relatively small numbers. So a big small number would be 0.1 to 0.001. For these guys that are weak bases and weak acids, you'll probably get a number like 0.0001 to anything that's even smaller. Let's say 1.0 times 10 to the negative 12. Once we start getting negative 12s and negative 15s for your exponent, those are really, 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 really small numbers. Okay? But they would make sure in a test not to give you like 0.1 versus 0.01, because those are relatively big numbers in comparison to what we're used to. So the type of question that you could get is they could give you something like, they could say, you know, an acid has a Ka of 0.13. And they could say, is this, or which acid, take that back, which acid could this be? Okay. Now, you would never need to know the exact Ka or Kb for any acid or base, but since this would be a multiple choice question, let's say your answer option A is HCl, your answer option B is HF, answer option C is, let's say, H2S, and answer option D, let's say, is HC2H3O2. Okay, so you get a bunch of different acids. Now again, you won't need to know specifically what acid has a pH of 0.13, but 0.13 is a relatively big number, especially in chemistry terms. Usually we deal with numbers that are like 10 to the negative 9 or really, really small. So 0.13 is not too small, which means this is probably from a strong acid, okay? Which is then going to test your knowledge of, do you remember what the strong acids are? Remember, there are 6 of them. Of those 6, HCl is the only one that's on your list of 6. So more than likely, the answer would be this one, because this is a bigger Ka, larger number, stronger acid. These guys here, these are all acids that are not on the list of 6. So these are all weak acids. So we would expect their Ka numbers to be really, really small, like 0.0001 or something like that. Okay? So that's why it's really important to know what is a strong acid versus what is a weak acid. Or a strong base versus a weak base. Okay, so that's pretty much all for 19.3. So 19.4 deals with neutralization reactions. Actually, 19.4 and 19.5 deal with neutralization reactions. One thing to know about neutralization reactions, they are just special types of double replacement. Okay? And what we do for neutralization is we take an acid and a base, combine those together, and they always make water and a salt. Now, when we say salt, we don't mean NaCl. We mean an ionic compound. So a salt is technically any metal with a non-metal. Okay. Now we'll look at an example. So let's say, and it doesn't matter the acid or the base. You can add strong, weak, doesn't matter. We just need to add an acid and a base. So let's say we take HCl and LiOH. So HCl plus LiOH. And we want to add those together. What will actually happen is the hydrogen from the acid and the hydroxide from the base, those are what come together to give us water. So water you can think of as HOH or H2O. We get a hydrogen and a hydroxide. Okay. Now the other parts that are left over, the metal from the base and the non-metal from the acid, those come together to give us the salt. And we said a salt is just a metal and a non-metal. So our salt would be LiCl. Okay. That's our neutralization reactor. So the hydrogen from the acid, hydroxide from the base make your water. The metal from your base and the non-metal from your acid make your salt. Okay. Where this is important is we would need to, and we can determine what type of pH the final solution would be. Because if you notice, this is something with water. It's probably going to be a liquid. It's probably going to be mixed in like a mixture. So we could actually figure out the pH of that mixture if we know the acid and the base. Like if they're a strong acid versus a weak acid, strong base versus a weak base. So if we look at this, HCl is one of the strong acids from your list of 6. LiOH, well, lithium is from your first column. That's one of your strong bases. Strong bases have metals from the first column, first or second column. So anytime we add 2 strong things together, so a strong acid and a strong base, we make a neutral salt. That means if we were to dissolve that salt in water, it would have a neutral solution. It's probably around a pH of 7, because the strong and the strong kind of knock each other out. Let's say we did a different example. Let's say we kept HCl, but let's say we changed this base. Let's say we changed the base to barium hydroxide. Okay, that would just mean that we change our salt. Our salt would now be BCl3. And now we probably won't have a neutral salt anymore. We have a strong acid, boron is not from the first 2 columns, so that means this is a weak base. strong acid and weak base, that base is not strong enough to knock out all that acid. So the salt that we make is going to be slightly acidic. It's going to be an acidic salt. So if we were to dissolve this salt in water, that pH would be slightly acidic because there's some leftover acid that wasn't completely knocked out by the base. Okay? So let's try another one and see what happens. So you can kind of see with these neutralization reactions, depending on what things you add together, that salt that you make in the end could either be neutral, it could be basic, or it could be acidic. So let's say, as another example, that we take HNO3. All right, let's do this guy. Let's take NaOH, and let's take HF. Now we know they're going to make water, because hydrogen from the acid and the hydroxide from the base is going to give you HOH, or water. And then the metal from the base and the non-metal from the acid are going to give you what we call the salt, so NaF. Okay. So from there, if we were to look at what we have as far as weak versus strong, start here. Sodium is in the first column, so this is a strong base. HF is not one of those 6 from your list, so this is a weak acid. So if we skip over here, we can try to predict what will happen with their salt. So if we have a weak acid and a strong base, this acid is not strong enough to counteract all of that base, so this would end up being a slightly basic salt. If we were to dissolve it, it would give us a pH that's probably above 7, something that's slightly basic. Okay. Now, what if we were to change this base? So we did strong and strong, you get neutral. Strong acid, weak base, you get acidic. Weak acid, strong base, you get basic. So whoever's strong kind of tells you how this guy's going to behave over here. But what do you think happens, let's see, when we do 2 weaks together? So let's say we have a weak acid, and let's say we have a weak base. So this is a base that does not have a metal from the first or second column. So this is a weak base. Okay. So our salt would be PBF. Okay. Now, if you have 2 weeks together, we really actually can't predict anything. So we'll say, cannot be determined. Now, technically, we can determine if it's going to be acidic or neutral or basic, but we would have to know the exact amount of each of these we're adding together. Because they're both 2 weak, we really need to do a little more kind of experiments to be able to predict anything about the salt. So when you have 2 weak bases or a weak base and a weak acid together, we can't really predict anything about the salt. But if we had a strong acid and a weak base, we could say that that's going to be acidic. If we had a weak acid, strong base, it would be basic. If we had a strong acid, strong base, it would be neutral. So just be comfortable, again, with knowing what's a strong acid, what's a strong base, and what are the weak acids and what are the weak bases. Okay. All right. So those are neutralization reactions. You're just taking an acid and a base. Now, one thing that we do in chemistry, and you guys may have done a titration lab, titrations are experiments that you can do to help determine the concentration. So titrations help you determine a concentration, okay, of an acid or a base. Okay. So one thing to keep in mind is this, and you may be able to YouTube and find a pretty interesting link if you didn't do the titration lab in class, is that we usually add a little chemical called phenolphthalein, and it turns pink in basic solutions. So when the solution turns basic, it turns pink, and that tells us when we can stop our titration. But titrations are just important to help calculate concentrations. I'll show you this equation. This is an equation that you'll be able to use if you're given any type of titration problem where you have to find the concentration of an acid or a base. I'll go through and define what each of these variables mean, and then I'll show you kind of a quick example. M is molarity. So remember, molarity is moles over liters. They may end up giving you the molarity, but clear here. But M is molarity. So the way that this calculation works is on this side, this is going to be all the acid information. On this side, this is going to be all the information from the base. But for both of them, the big M means molarity. We just would need the molarity of the acid or the molarity of the base, but usually for one of these big M's, we don't know, and that's what we're solving for. V is the volume, but it has to be in liters. So this V has to be in liters. Can't be in milliliters. You got to convert it into liters. Now, Na, same over here for the base. If the base has to be in liters, we can't use milliliters. Now, Na is the number of hydrogens in the acid. Okay? So if you have something that's diprotic that has 2 hydrogens or triprotic that has 3, you have to know the amount of hydrogens. Okay, and that's what the Na value is. And B, since this is for the base, is the number of hydroxides or OHs in the base. So if you have something that has more than 1 hydroxide, you put a 2 or 3 or whatever number here. So as an example, let's say you had H3PO4 for your acid. That means that you'd put a 3 in. So your Na would be equal to 3. Let's say you had calcium hydroxide for your base. Well, in that case, your Nb would be 2 because there's 2 hydroxides in this group. Okay? All right, so let's look at an example, and I'll throw it up here above it, and we'll kind of walk through it. So let's say, just give me a second to write out type of problem that they could give you. Okay, so let's say you have 450 milliliters of a 3.5 molar solution of H2SO4 is used to neutralize. Now they may instead say used to titrate, but either way, 315 milliliters of lead hydroxide. What is the molarity of the base? So if we look at this equation that we have here, let's figure out what we need to plug in. So that is our volume for the acid. So this is the volume for the acid. This is the molarity for the acid. That tells us the acid. We can then figure out the N value that we need to put in. This guy here, that's the volume for the base. And this tells us the base, so we can use that for our NB value. So let's start plugging things in. So the way that this would work is the molarity of the acid we have is 3.5. So we're just putting in the molarity. The volume of the acid we also have is 450 milliliters, but remember, we got to convert it into liters, so it's 0.45. And then the Na is the number of hydrogens that the acid has. So the acid is H2SO4. It has 2 hydrogens, so we put a 2 in for the Na. Now for the base, we don't know the molarity, so I'm just going to put a little Mb to remind us that's the molarity for the base. The volume of the base we used was 315 milliliters. We got to convert it to liters, so 0.315. And then the base, for the NB value, we need to know the number of hydroxides in the base's formula. The base has 4 hydroxides, so we just put a 4 there. Okay, so to solve for MB, or the molarity, we would want to multiply all 3 of these together on the left side, and then we'd want to divide by 0.315 times 4. And so this calculation here would give us the molarity. So 3.5.45 times 2 divided by 0.315 times 4. So I just divided both sides by this guy here. And that's pretty much how you use it. I mean, they could switch the wording up on you and instead give you all the information for the base and have you find the molarity of the acid. That's fine. In this case, you would just have the M on this side, but you're always just dividing. When you set up your equation, you're just dividing to find your final answer. Okay. So hopefully that's a little more straightforward. This is a little more like 19.4, 19.5 if you were to get any calculations based off of titrations. But that's how we set it up. So just knowing that equation, you'll be able to use that every single time. The last thing that will probably be on your test are buffers. Now there aren't really any calculations related to buffers, but you should know what a buffer is. So a buffer basically protects the pH. So if you think about when someone may buff the floors or buff their car, they're putting a layer of wax there to protect the car or the floor. A buffer can protect pH. And we have lots of buffers in our body to make sure that our blood stays around a pH of 7 so that we don't have our blood become too acidic or too basic. So the way that they work, a buffer is made up of two parts. So I'll just say has two parts. It has a weak acid, and a buffer is a solution. It's a liquid. So it's made up of a weak acid, and it's made up of a salt. Okay, so both of those things together have to be included in the buffer. And the reason why they have to is because if we have, let's say, something basic all of a sudden that comes in, the buffer is able to neutralize or get rid of things that may change the pH. So if something is too basic, so let's say we drink bleach or something that's really basic, what actually will happen, or what our body will try to do, is the weak acid part of the buffer, it will eliminate bases. If we were to drink something that's really, really acidic, what our body does to make sure our blood doesn't all of a sudden become acidic is the salt part of the buffer helps to eliminate acids. So no matter what we encounter, whether it's something acidic or basic, something in the buffers in our blood is able to counteract it to make sure the pH stays about the same. Now, what do we mean by that? So let's say we have a pH that is 5.5 and we want to protect it. So we would add a buffer to that mixture. And what that buffer would do is no matter what we add to the mixture after we add the buffer is going to protect that pH. So let's say 5 minutes later, after we add the buffer, we then add something that has a pH of 13, so something really, really basic. Well, what would happen is that this pH should shoot up really high, because if it was 5.5 and we add something that has a really high pH, then the pH would probably get pulled closer to 9 or 10 to kind of average those two numbers out. But that doesn't happen. The buffer actually counteracts that pH to make sure this pH doesn't change. Now, it may change a little bit. It may change to, let's say, 5.8. It may get a little bit higher, but it's not going to dramatically change like it would if the buffer wasn't there. Same thing happens, let's say that we have that mixture with the buffer and we add something that has a pH of 1, something really, really acidic. Well, what would happen if we didn't have the buffer is that this number would want to drop, probably closer to like 3, somewhere in between those two numbers. But instead of doing that, what actually may happen is the buffer protects this pH and it may lower the pH just slightly, maybe to 5.1, but not significantly. So that's the beauty of the buffer. It kind of keeps the pH around the same value. Now, it doesn't mean it's not going to change at all, but it's not going to change as much as it would if you didn't have the buffer. Just like if we protect the floors or protect our car with wax, you still may get little dings and scratches, but it may not be as severe as it would if you didn't have that protective layer of wax there. Now, one thing to keep in mind for the buffer, buffers aren't, they're not 100% foolproof. Meaning, if we were to add a ton of acid, or if when we added this, let's say we had a small mixture, let's say this was only 30 milliliters, and let's say we added 100 milliliters. So let's say our mixture was 30 milliliters, let's say all of a sudden we add 100 milliliters of something that's a pH of 1. Well, in this case, we have way more than we do of the buffer. So the buffer is really not going to be able to protect that pH. This pH may really change, and it may really change drastically. It may drop from being 5.5 to being 2.5 as an example. And that's just because if there's too much acid or too much base added, the buffer can only do but so much. Now, if we only added a little bit, so instead of adding 100 milliliters of that acid, let's say we only added 10, and we have 30 milliliters of this buffer, then the pH may be closer to about 5.1. So we do have to take into account the amount of acid, the amount of base that we're adding, because the buffer can only kind of counteract so much. If it's so much acid in comparison to how much buffer we have, it's not going to really be able to help you. But in general, buffers help to protect the pH from changing. Hopefully this was helpful. So this reviewed 19.2, 19.3, 19.4, and 19.5. There's another video for 19.1 that goes over the definitions of acids and bases, as well as how to name them, that may be helpful to look at to review for your test.